So we continue with the continuous time Markov chains by looking at the birth-death processes. Birth-death processes. So by definition, a birth-death process is a continuous time Markov chain where transitions occur only between neighboring states. For instance, if you have the state space 0, 1, 2, 3, transitions like birth will be move from n to n plus 1. So a birth is a step ahead with rate lambda n, whereas a death is a step backwards. So that's from n to n minus 1 with rate mu n. So it means you can move from 0 to, okay, let's start from 1. You can move from 1 to 2, that's a birth with rate lambda n. And you can move from 1 to 0, that's a death with rate mu n. That is basically the summary of the birth-death process. A step ahead is birth, a step behind is a death with different rates like that. Now, talking about the transition rates now, in fact, I believe this is what we've been seeing previously in what we know as the generation matrices, right? Because you see that minus lambda lambda and mu minus mu kind of thing in those matrices like that. So transition rates. So at state n now, the birth rate is lambda n and death rate is mu n. So that the transitions are like this. From n to n plus 1, it happens at rate lambda n. From n to n minus 1, it happens at rate mu n, like that. Okay, that's basically what the birth death process is about. So talking about the generation matrix now, the infinitesimal generator matrix Q can be said to be minus lambda naught, and all that's 0. Whereas you have mu1 minus lambda 1 plus mu1, lambda 1, 0, 0. Then you have 0, mu2 minus lambda 2 plus mu2, lambda 2, and all that all the way down. Now you discover that just true to type for a generator matrix, if you add all the elements on the row, it goes to 0 minus lambda naught 0, every other thing is 0. Then mu1 minus mu1 0, minus lambda 1 plus lambda 1 0, every other thing is 0. Then mu2 minus mu2, if you open this up, that's 0, minus lambda 2 plus lambda 2 0, everything goes to 0. So this is typically what this looks like. So the birth death process just goes like that. So then for the Kolmogorov forward equations, which we already saw in a previous video, so we say let p sub n of t be px of t equals n. Then we say that the p sub n dt is lambda n minus 1. That is a step backward into Pn with probability Pn minus 1t plus a step forward mu n plus 1, the rate of moving forward with multiplied by the probability of moving forward at time t minus lambda n plus mu n. That's the current state now. So the current state, subtract the current state from add up the probability, the rate of moving to the previous state with multiplied by the probability plus the rate of moving to the next state multiplied by the probability minus the summation of the rate of current state, the rates of moving forward and rate of moving backward multiplied by the probability at the core of the current state, like that. And then we have special cases where we can say we have pure birth processes. So for pure birth processes, mu n is equal to 0. That is the possibility of moving, the probability of moving. Let's see back here again. Lambda n is the birth rate, right? So we are simply just talking about purely births. That's why, so no death. So that means mu is 0 in that case of a pure birth process. So mu is equal to 0. And when mu is 0 like that, you have lambda n minus 1, pn minus 1 minus lambda n pn. But for a pure death process, lambda n is equal to 0. So for a pure death process, there's no birth. For a pure birth process, there's no for a pure birth process, there's no death, so mu n is 0. For a pure death process, there's no birth, so lambda is 0. And if lambda n is 0 like that, okay, all this will just go this way. So lambda n is 0. And then we also have a queue, an MM1 queue. So a queue with one server, right? A queue with one person attending to the people on the queue. That's also a very good example of a special case of, oh, okay, I think I've skipped some things. So for special cases of a birth death process, we have pure birth process where death is 0, the rate of death is 0, pure death process where rate of birth is 0, and we have a linear birth death process where lambda n is lambda times n, and mu n is mu times n. That's a linear birth-death process. Then we also have the MM1 queue. You have people in a queue being attended to by just one person. So in that case, now lambda n is lambda and mu n is mu, like that. So here the lambda is the arrival rate, while mu n is the service rate. So when people arrive, it's like a birth. When people are serviced and they leave the queue, it's like a death process, like that. Then we talk about the steady state distribution for birth-death processes. So we define pi n to be limit as t tends to infinity of the probability of the current state. And then we can balance equations by having lambda n minus 1 pi n minus 1 equals mu n pi n. And then we have a recursive relation off of this, that um, lambda n now is lambda n minus 1 over mu n multiplied by pi n minus 1 as a recursive formula for the steady state distribution of a birth-death process. So in general, the general form, we then have pi n to be pi naught, all right? Um, you know, taking pi from k equals 1 to n of pi k minus 1 all over mu k. So obviously here we are taking we're taking n to be k plus 1. If n is k plus 1, so it means that we have k plus 1 minus 1, that's pi k. Or better still, is n k there? This is pi k minus 1. Okay, yeah, maybe n is just k, right? Yeah. So you're multiplying pi n minus 1 mu n. So the general form translates to pi n equals pi naught. Pi this sign means multiplying all this whole thing from k equals 1 to n. That means you have pi k minus 1 over mu k. So as you keep changing the values of k from 1 to n, you multiply all those values together like that. And then you can then have the normalization that the summation from n equals 0 to infinity of pi n is equal to 1. That means that's why we always have it that all the pi's, we have this for steady distribution, right? So that all the pi's always add up to 1, like that. So we have a very good example in an MM1 queue, that is a queue where there's only one person servicing the queue. So if the arrival rate is 2 and the service rate is 3, then we can define that we have a stability definition. In the next video, we'll be looking at queuing models in serious depth. So you want to watch out for that in case you want to learn about queue theory. So you have rho to be lambda over mu, which is 2 over 3, right? So that talks about how balanced the system is. So as far as rho is less than 1, we can say you have a stable system. If not, if the arrival rate is bigger than the service rate, you have an unstable system, and there can be chaos if it gets to a point, right? So in step 2 now, you have the steady state distribution where pi n is now 1 minus rho raised to power 1 minus rho into multiplied by rho raised to power n. So pi n is now 1 over 3 into 2 over 3 raised to power n, like that. And then we have values. So pi naught can then be 1 over 3, pi 1 is 2 over 9, pi 2 is 4 over 27, and things keep going on like that. Okay, so we can then simulate that using with Python code, right? So for the case of an arrival kind of situation like this, in fact, I think I can do this as this. So this can just be pi sub n with this here. So I think we can also make this into like an uh F string. I think that should work. So that this now becomes like proper pi sub n here. Let's see how that comes out like. So here now you have the states. So state n. So starting from 0 to 8, and then you have the probabilities of all of that happening like that. So these are like arrivals in that state now. Okay, this isn't working. So the pi n came out, but I think there's something we need to do with F strings. Do I remember what F strings should look like? Yeah. So, mm, invalid escape. Am I trying to escape? What if we do double? Does it solve any problem? Yes, it does. Excellent. Yeah, that works perfectly now. Yeah. So we have the probability pi n there, and then we have the state. So that's probability of arrival and things like that. So we have that. So we will learn more about this in the next video where we talk about queuing models, queuing theory. So now we have an example, a general birth death process. So lambda n is 2, mu n is n, for instance. So we then have pi n to be pi naught 2 raised power n over n factorial. If we normalize that, we have summation from n equals 0 to infinity of 2 raised power n over n factorial. And that comes out like e raised power 2. So that pi naught is actually e raised power minus 2, like that. So, and then the final result is something like pi n equals e raised power minus 2, 2 raised power n over n factorial. And this is a Poisson distribution with mean 2, you know. You have mean 2 raised power n, e raised power minus 2, all over n factorial. So the mean is uh, lambda t, right? That's arrival rate multiplied by time. So that's why all these kind of processes follow Poisson. So if you simulate this now, you get all these values for from 0 to 9, like this, from 0 to 9. So you have those different values. And one thing we notice is that once you are getting once n is beginning to be greater than 2, the values become very, very small. So then we have mean and variance for birth and death processes, of which Q theory is one of those examples, MM1, for instance. So for in the general form now, the expected value of n is summation of n pi n, and then for MM1 result, that's a queue with just one server. So you have uh, E sub n, the expected value will be rho over 1 minus rho. You will understand this better in the next video. Then you have variance of n, which is rho over 1 minus rho squared. And then you have an example. So you have 2 over 3 over 1 over 3. So the expected value is 2. That's like the expected value of arrivals based on this kind of values now. If the arrival rate is okay, rho now. Rho is actually arrival over service rate, you know. So 2 over 3, like that. So that 1 minus rho is 1 over 3. Then for 36.8, now you have the simulation idea. So at state n now, you have total rate, lambda n plus mu n, and waiting time is exponentially distributed with parameter lambda n plus mu n. And you have transition probabilities like birth with probability, that's lambda n over lambda n plus mu n, and death with probability is mu n over lambda n plus mu n, like this. And then we can have all of that simulated using this Python code right here. Okay. And of course, you want to see this. And when you have all of this like this, then you have the bed there simulation. And as you keep running it, it keeps changing for sure. So it keeps shifting shapes because it's a stochastic process. It's a system evolving over time with randomness, with uncertainty, like that. So that's the bed process simulation. So what's the applications of bed processes include, like we've already seen, bed processes appear in queuing systems, population dynamics, epidemic modeling, reliability engineering, and chemical reaction systems, like that. And then that takes us to the practice problems on birth-death processes. Define the birth-death process and explain why it is a special case of a continuous time Markov chain. Of course, what we know is that in a continuous time Markov chain, you move from one step to another. But for a birth-death process, you can only move between adjoining states. You know, you go forward, that's a birth. You go backwards, you go forward, that's a birth. You go backwards, that's a death, right? So you can write down the generator matrix Q for a general birth death process. That's like the usual minus lambda lambda, then mu minus mu, that kind of thing. Explain the meaning of the parameters lambda n and minus mu n. This is the rate of moving from n to n plus 1, and that's lambda n. The rate of moving from n to n minus 1 is mu n, like that. So this is birth and this is death. Then talking about Kolmogorov equations, define the forward equation for Pn of t. Derive the forward equation for Pn of t, which is the Pn of t dt, blah, blah, blah. So we saw this kind of thing before. Write the forward equations explicitly for states n equals 0, 1, 2. So you just substitute those values and make it clear. Then you have the steady state analysis. Show that the steady state probability satisfy lambda pi equals mu pi, like that. Then derive the general formula of this. Explain how to determine pi not using normalization. Then for MM1Q, so for lambda is 4, mu is 5, compute rho. Of course, rho will simply be lambda over 5. That's 4 over 5, which is 0.8. And determine pi n. Of course, just substitute like before. Then compute pi naught, pi 1, pi 2 for the above system. Then find the expected number of customers. Then En is rho over 1 minus rho. So just evaluate based on the rho you've got. Then general bed death processes. you have lambda n is 3, mu n is n plus 1. Find pi n. We follow the kind of thing we did before. Sure. Whether the process in problem 12 has a valid steady state distribution. And then you have Poisson type example. Given lambda n is lambda, mu n is mu is n. Show that pi n is all of this, which is Poisson, right? Then identify the distribution and compute its mean. The distribution is simply Poisson. So, and the mean is, of course, the mean will have to be this lambda now. Then you talk about stability and convergence. So prove that an MM1Q is stable only if lambda is less than mu. That means that lambda over mu is less than 1 for sure. Explain what happens when lambda is greater than or equal to mu. When lambda is greater than or equal to mu, there's going to be instability in the system because you have more people arriving than they are being serviced. So the queue is going to be long and it's going to be chaotic subsequently if there are no care, if care is not taken. Then you have simulation-based problem. Simulate a birth-death process with lambda 2 equals 3, plot the sample path. So of course, this is so the Q, the generator matrix will just be minus 2, 2, and then 3 minus 2. I mean 3 minus 3. Then modify the simulation to estimate empirical probabilities per n. Then for advanced thinking, I'll consider lambda n is this, and define conditions for extinction, discuss long-term behavior of the process. So try this out. If you have issues with anyone, let me know in the comment section, either on Facebook or on YouTube, and I may be able to solve any of the problems that you may need clarification on. So with this, I come to the end of this interesting process about birth-death processes, which talks about moving between adjoining states. If you move forward, as a birth with a rate lambda sub n. If you move backwards, as a death with rate mu n. Let me know how helpful this is for you, and there's something else you'd like me to try out. Feel very free to let me know. Okay. If you have subscribed already, I thank you very much for doing that. If you have not, of course, go ahead, subscribe, hit the notification bell also, so you can always get alerted each time a new video is released. You can also click on join to become a member of the channel. That gives you special privileges like getting to see some videos first, or being the only one to see certain videos because you're a member of the channel. You could also request for PDF copies of my notes as a member of the channel. We can also hang out together to discuss whatever might interest you on this channel, be it mathematics, data analysis, data science, scholarships, machine learning, whatever. If you are, we can hang out physically if you're in the same geographical location at any point, and we can hang out virtually also. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Watch out for queuing models in the next video, which will be the last video as far as continuous time Markov chains are concerned. And then from there, we'll move on to, I guess, renewal processes, So watch out for that video, next video on queuing models. Till I come your way again, keep doing maths right. Bye.